everyone, my name is Shahbaj Mukul and my project is called Manufacturing Error Code Predictor. So for the introduction, we will go over some context of the project, and this is inspired from one of the internship projects that I worked on. So we are imagining in a production facility there are um, production downtimes, and downtimes basically means when there is no production ongoing, and during a downtime it disrupts the factory productivity. And machine PLCs, or PLC basically means that the programmable logical controller, and that is present in every major machines, can detect the downtime, basically when the downtime started and when the machine went back up again, it can detect the end of that downtime, and that downtime gets sent as a notification to the technicians, because the PLCs cannot or are not smart enough to identify the cause of that downtime. So a technician has to manually assign the group and code for the downtime. The group basically means that it's a machine that's responsible for the downtime, and code is basically the reason behind that downtime. So here is a visual illustration of what I just talked about, and here we have the production machine, and every machine has this PLC, and whenever the production stops, it can detect the status of the downtime, and then it will send that notification to the server, and then the server will send it to the technician. Basically, this is how the notifications are generated. But as we saw, that this is a very time consuming problem, but also we can utilize machine learning algorithm to make this process efficient, based on considering the fact that this has been done for a long time. There is a historical data set where the notifications were completed by technicians, and there may be a pattern that we can use to train a model. So for our data set, since we did not have the real world data for that, we basically have to synthetically generate records to train our model, and we just decided to generate 15,000 model, and some of the features for that model, the records, is the machine type, location, start and end time, and the duration of that downtime. And the target group for that is the group which is the system and the code, it's the error. And we have to also introduce some biases into the data set, because in the real world there may be some problems that occur more often than others. So basically we also have to recognize that in our data set, and have that model train on that. Otherwise we can't just train a model in random data set and have it understand a pattern, because in randomness there is no pattern. So to prepare the data, we had to perform some pre-processing steps. We first shuffled the data to prevent pattern leakage. Then we performed one hot encoding for categorical values, and then we performed standardizing the numerical features, so that all the model considers all the data in a familiar unit. So for the model overview, we selected the random forest classifier as our model that we will use to train on our data, because the random forest classifier handles high dimensional data, as we explained that our categorical data are not numerical, so the model has to understand those after we convert it. But it also reduces overfitting. After that, it also provides insight into the feature importance, which is very important in this case, where we want to recognize the pattern ourselves as well. So for the training data, we decided to take 80% of the generated data, which is 12,000 records. And after we trained the model, we decided to evaluate based on these four matrices. First one is accuracy, precision, recall, and the F1 score. we find out that the strengths for the model was that it is very accurate for majority class when detecting a group or code is not the cause, but its weakness is that it struggles when detecting when like it can detect if that group or code is the cause. And we tested on 20% of the generated data, which is 3000 records. We find out that the feature importance were start time, end time, and duration. But we also find out that the majority and minority class had imbalance, and this is the reason being that we introduced the biases that we talked about earlier. And lastly, it predicts not this better than like this. So like I talked about, it can detect if a group is not the cause, but it can't, it is very bad at predicting if the group is the cause. So this was not required, but we wanted to demonstrate how this can be used in a production environment or something like that. So to deploy that, we created a simple app where it takes input of machine type, location, start time, and duration, and it outputs a probability of certain group and code belonging to that record. And it will use that model that we trained. We decided to save the model as pickle file, and it uses that to predict. So here is what the UI looks like. The user enters these three information using the drop downs or typing, and the application then uses the loads typical file and then uses that to predict the probabilities of certain groups and code, which is more likely to be the cause for the downtime. And to conclude our model prediction, we find out that we had some challenges with the class imbalance, as I talked about before. Some of the learnings that we found out was that we succeeded using the random forest because of the predictive accuracy. We will go over those in the Jupyter notebook. We could fine-tune the feature importances as well. The random forest leans for the majority class, and we can find more insights into this if we test on real-world data with balanced classes. And for the project potential impact, we think that there may be a huge impact on business side of things. It can provide a faster technician response time by giving them probability of the UI that I just showed, and have them decide if this is the correct group and code, where they wouldn't have to guess around. But the businesses can also take preventative measures by looking at the model's outputs and then seeing a pattern of which are the most common groups in code and what maybe which downtime may be next, and then they can take preventative measures to reduce that, and that will equate to higher productivity and profitability. But some of the improvements we see that can be done is by training on real data set, and then it can also we can also do a combination of other algorithms to improve the class 1 scores, and then fine-tuning the model after evaluation, so that we can determine which ones are the cause. And we are pretty much running out of time, but I'll quickly go over the Jupyter notebook file. Basically what we talked about are some of these things listed here, some of the libraries that needs to be installed before you can proceed. And here's how we are generating that downtime. And as you can see, we have group and code right here. Here's how we are interjecting biases. So here are some This is a bias for duration. Some groups can have some issues, may take more time than others to fix. Some code are more likely to happen than others, basically. Since we did not make it random, we have most time consuming issues right here. This is the visualization of the data with the durations. We don't have any missing values, but this may be important when we are working with real data. And then after that, we encoded the categorical variables. This is where we standardize numerical features. So that we have a same metric for evaluating all that. We are splitting the data into 80 to 20. And then model selection, we selected the random forest. Evaluating, we evaluated the model on the test data set. And this is what we were talking about when we said where the strengths and weaknesses for the model is. But if we take a look at this, accuracy for the model for all the groups and code is pretty impressive, as it is like over 90% into almost all cases. But the issue here is that when it is class 0, it performs really good at 0.93, and in F1 score it is 0.95. but when it is trying to detect if the downtime is the air system, it fails to do that pretty much 50% or 41%. And that is pretty much similar for all the cases. In some of the cases it is pretty bad. It's 0.14 in the F1 score, and precision is 0.21. So it performs really poor, but one of the reasons being is that we have many nodes of codes rather than groups, so it may perform better on groups because we only have like very limited, maybe 15 groups, but for codes it is tied to the groups, and it is dependent on the group that is selected. So that's one of the reasons why the code is also low. Here's the rundown of what we talked about in the slides as well. We also did not go over the confusion metrics, but that is also available for someone to take a look. But if we just skip over all this. Here we interpreted what some of the top features for predicting the all the group or codes are, and we see that for air system it is duration. It varies for some of them it is the same. So for this one it is feature, the end time is the most important, start time is the most important, the duration. So for codes duration is third, and that's the reason being we have more codes than group, and code is dependent on the group. And here is the visual illustration of that for group prediction. And if we go skip over all of this, we have top 7 features for code prediction right here. And just for fun, we decided to visualize the single decision tree, but it still came out to be really something. It's something to look at. And for deployment, we decided to save that Z4 model. Decided to call this Z4 as the Downtime model. And here is a simple Streamlit app that we use to predict. So I will show how it works. So there we go. If I just refresh it, I have this UI where I'm able to select a machine type, machine location, and duration. Let's say 32 minutes, and from 500 minutes from midnight. And if you click predict, you see this probability distribution. And again, it's not very accurate. It's just to showcase the capability of what can be done. And that is the presentation. Thank you.